Well, thanks very much for having me, and I would like to extend a special thanks to Professor Terence Tao for the Hagoroma chalk. Um, so, uh, let's start with this commuting scheme question. So I'm going to start with something easier. Consider matrices, n by n matrices, let's say over the complex numbers, and I'm going to insist that they square to 0. And so this is a bunch of, what do we have here? We have ring and n squared variables, the matrix entries, and we have n squared many homogeneous quadratic equations in those variables. And I want to say, when you consider this set, there's actually some secret equations that hold. So what do I mean by a secret versus a non-secret equation? So the non-secret is I could take these polynomials, take the ideal they generate. Just linear combinations of these things where I'm allowed to multiply by other arbitrary polynomials. And those are sort of the obvious ones. But the secret ones come from the following observation. M squared equals 0 implies that m is nilpotent, implies that the trace of m is 0. And so this is a linear equation. How are you supposed to derive a linear equation from a bunch of homogeneous quadratic equations? And the answer is, if you take the right combination of them, you won't learn that trace of m is actually 0, but you will learn that trace of m squared. Not trace of m squared, obviously, but trace of m squared is 0. So that might seem like a silly thing to worry about. It becomes more worrisome if you're thinking about, say, numerical analysis, where when somebody tells you that something is 0, they really mean that it's very small. Like if I have a 1-by-1 matrix with a number in it, and I tell you that that's very small, you say, okay, that's like only a millionth. But that doesn't imply that then when you take the trace of this matrix, that's like a millionth, right? You can only find out that it's like 1,000th. So you want to know if there are extra secret equations that hold on your set, you'd like them to be specified out loud. And it turns out in this case, if you take this ideal, if you take the ideal of this guy, so these n squared many equations, and you take the radical of that ideal, then it is indeed generated by the obvious ones and the trace. Okay, so that's a solved problem. And the unsolved one, and one reference is Hochster 84. The unsolved one is, what if I consider pairs of matrices x and y, and I demand that they commute? Are there secret equations that hold on this set? Nobody knows. Is the ideal generated by these n squared many quadratic equations a radical ideal? Nobody knows. So we can compute up to like n equals 8, I think, and find out that no. So there are algorithms that will take an ideal and compute its radical, and up to like n equals 8, there are no secret equations. So Terry was asking if we could compute for small numbers, and we can. There are certainly people conjecturing that that this ideal is radical. There is one guy who has put more than one paper on the archive asserting proofs of this. I'm afraid that his later papers asserting this do not explain what was wrong with his previous papers asserting this. So so that guy, I'm pretty sure, conjectures that that this ideal is radical. I mean, there's some other things to know here. Like, we do know that that the set defined by this is irreducible. There's a stronger thing, and we know that it's generically reduced. That if you, I want to get into the definitions of those, but if we knew more things on this, like that this is Cohen-Macaulay, then that would do it, because Cohen-Macaulay plus generically reduced gets you reduced. So anyway, so I'm just going to pose it though as a question rather than as a conjecture. Do there exist secret equations? Okay, so alas, I'm not going to be answering this question, but this was my motivation for considering the following related. So I said, let's let row check of T be the diagonal matrix with powers of T down the diagonal, 1 through n. Let's let x prime be x times row check, and y prime be y pre-multiplied by row check inverse. And then you could rewrite the equations xy equals yx in terms of these. So this is a linear change of variables that I'm performing here, because for any particular t, I'm just linearly rewriting x prime in terms of x. So it's not very, doesn't look very serious what I'm doing. And what's nice about how I set this up is that x prime y prime is xy, which is supposed to be yx, but that's now rewritten this way, is not y prime x prime, but is instead that with a row check here and a row check the inverse there, conjugated. So where I'm going with this is I'm going to take the limit as t goes to 0 of the equations, of those equations. And I'm going to get, so I had my n squared equations to begin with, these n squared, and I'm going to get n squared equations when I'm done. And what they look like is the diagonal of x prime y prime equals the diagonal of y prime x prime. And x prime y prime is lower triangular, and y prime x prime is upper triangular. Now, what I don't know is whether the original n squared equations were a Grobner basis with respect to a term order that would let me do this sort of thing. Well, I only know if you take these n squared equations and take the limit, you get those n squared. I don't know if there are clever combinations you could take of these where, as you take the limit, you manage to cancel off leading terms and powers of t and sort of see deeper into the limit ideal. I conjecture that this is, in fact, the limit ideal, that these n squared equations generate the ideal you would get by taking the limits of all uncountably many equations in the original ideal. Not quite. No, you can go the other direction. So if this guy is reduced and irreducible and of the correct dimension, then the original guy is reduced and irreducible. Yeah, so you can only go that direction. So when you do these degenerations, things can get worse, and things can go from reduced to non-reduced as you get sort of things colliding with themselves. So I conjecture. Well, okay, you asked about this is a conjecture of this. So I conjecture, in fact, that this is reduced and irreducible. So I looked at this and said, so I'm going to call, yeah, okay. So the conjecture that this is reduced and irreducible will imply that this is indeed reduced and irreducible. You need one more thing, which is trivial to check pretty much, which is that this has the same dimension as that, n squared plus n. But it does. It is. I do believe that there do not exist secret equations. So I hope that there are. I think that would be a much more interesting result. But I think it would be cool if when somebody tells you two matrices commute, you could say, ah, but do they also satisfy Allen's equation? So, yeah. Which, if you're working over a field, then one would imply the other. But if you're working over some ring with nilpotence, then it might not. Okay, so so this motivated me to define the lower upper scheme. Which is pairs of matrices. I'm not keeping the primes anymore. XY is lower triangular and YX is upper triangular. And so how much have I lost by not specifying stuff about the diagonal? Well, the matrices XY and YX always have the same characteristic polynomial. So if X is invertible, then they're conjugate matrices, but then by continuity, it's always true. So in particular, they have the same eigenvalues, but you can see the eigenvalues because they're triangular matrices. So you know for sure that that this guy has the same diagonal as that guy does up to permutation. Okay, so let me now define E-pi to be I'll take X and Y in the lower upper scheme, and I will ask that the diagonal of XY be a certain permutation of the diagonal of YX without repeats. Okay, so what am I saying? I first say inside E, let's take the open set where XY does not have any repeats along the diagonal. So that's some open set in E. Then I'm observing that that open set is disconnected, and this is one of the connected components. And then I'm taking that thing and taking the closure. Okay? So what I proved some long time ago now, I think it's 2005 maybe. Sorry about that. Anyway, it's called some schemes related to the commuting variety. And it was certainly approximately then. So what I proved is two things. One is that E is the union of the E-pi's. So there aren't extra secret weird components sneaking in here that come only when there's enough repeats. And that might sound like a crazy thing. Of course, that's not going to happen. But if you've ever played with like the Hilbert scheme of endpoints in 3 space, you know that it's crazy and can happen. Next, yeah, E is a reduced complete intersection. So there are no secret equations here. That's the reducedness. Complete intersection is that this guy has the expected dimension. So we start with 2n squared. We subtract n squared minus n. This guy has dimension n squared plus n. It's got the right dimension. Now, there's an action on this guy by lower triangular matrices cross upper triangular matrices. And the way it works is if you have a lower triangular matrix and an upper triangular matrix, and you apply them to a pair XY, I'm going to take X and Y and multiply X on the left by B minus and Y on the right by B minus inverse. And that's going to be good, right? Because one way the product doesn't care at all. And the other way, we're conjugating a lower triangular matrix by a lower triangular matrix, so it's staying lower triangular. And then the other guy is acting similarly on the other sides. Okay? So you should see this as the analog back in the commuting scheme. Here we had an action of GLN that we could, if X and Y commute, we can conjugate the both of them at the same time by the same element of GLN, and they will still commute. And as you degenerate, I didn't say how this limit works precisely, but as you degenerate this, you can follow that GLN, and it basically turns into this. Not quite, it turns into a subgroup of this, but you find out that not only does that subgroup work, this entire group acts. Yep, n squared plus n. The basic answer is no, in that, for example, so the easiest one is, so let me give you an example, which is EW naught. Okay, so E, the permutation like this. Okay, this is pairs of matrices. I might need a couple tries at this, but I think this is pairs of matrices where this guy looks like that, and this guy looks like that. Something like this, where you multiply one way and it's lower triangular, and you multiply the other way and it's upper triangular. In particular, this one is linear. So if it's not this, it's probably that backwards. But this thing is a component of E that's really simple. Whereas the component I want is at the other end of things. It's where the identity, and I have the identity hiding here. So, so that's to say that the varieties in question are very different geometrically. All they have in common is that their degrees are the same. Excuse me, their dimensions are the same. Terry points out that they're not empty, and I will say more than that. So let me parameterize them. So what I'm going to do is, well, okay, yeah. So I'll tell you some things that are really obviously in E-pi, which is if you take pi itself and pi inverse, you take that pair, then that's not obviously in here because so far we just have the identity on it. Okay, so fine. I'm going to multiply this by a generic diagonal matrix. Okay, so D in D, the diagonal matrices. Okay, so far, no, as written. You multiply one way, you get D. Multiply the other way, it's conjugated. Okay, so this is something that's inside E-pi. But E-pi is a component of E. E has this action of this connected group. Therefore, that connected group acts on every component separately. Since it's connected, it can't permute them. So that means if I take this and I hit it with B minus cross B plus, I know that's still going to be in E-pi. And if I take the closure, that's still going to be in E-pi. And in fact, E-pi is that. So it's not an orbit closure, right? But I've got this group acting, and it would be nice to just say I take a point and I hit it with this group and I get the entire E-pi. And I'm coming pretty close. I'm saying, well, you don't start with a point. You start instead with this very comprehensible set. Can I glue a Schubert and opposite Schubert to get my E-pi? I don't have a statement like that. The statement I will make a statement a little bit like that, but it's not that right now, which is so we had this guy E-pi living inside pairs of matrices, and we could then project to the two factors. We could say, what's X, what's Y? And this makes it very easy to understand what you get when you project. So if you project to the first factor, it's like throwing this away and then taking the orbit, right? So the action doesn't sort of mix the x's and y's. And so that's so you can, these maps are equivariant with respect to an action of B minus cross B plus on each of the two matrix spaces, one this way and the other one that way. So that means I can take this guy pi, hit it with this thing, and I know what I'll get down here, which is a thing called x pi bar, not equals, inside, the matrix Schubert variety. I was supposed to write bigger. Matrix Schubert. So that, by definition, is a permutation matrix times B minus and B plus, take the closure, inside matrices. Okay? Meanwhile, if you project it the other way, then the B minus and B plus are acting the other way, and we have this pi inverse, and so we get pi inverse W naught X. That matrix Schubert variety itself conjugated by W naught. Okay? And there's no particular relation between these two varieties. For example, I mean, they've got the same dimension, but as it happens, kind of an accident. So this guy always has one dimension, which is n squared plus n. This guy, the dimension, the codimension is the length of pi, and this guy, the codimension is actually again the length of pi, because that is the length of pi inverse, which is also the length of pi inverse conjugate by W naught. Nope, absolutely not. So for example, let's take pi to be 213 in S3. And then this guy will be a degree 1 variety, and this guy will be degree 2. And this thing is just something that lives inside the product of those two. Okay, so I've been thinking about matrix Schubert varieties for quite a while, and one thing I want to tell you about them is if you take the initial terms of the equations defining x pi bar, so theorem by me, and I'll write out his whole name because there are too many Millers out there. Ezra Miller, 5. If you take the antidiagonal terms, which I'll show an example in a minute to say what I'm talking about here, of the equations defining this, you get a union of coordinate spaces and it'll be a union over pipe dreams for pi. So let's do an example and then and see what these are. So the example up here. Yes, of the matrix Schubert variety. Yeah. So okay, let's start with a really easy example, which is pi is 132. So I'm starting with this. I have this B minus cross B plus. And what B minus does is downward row operations. So left multiplication is row operations. B minus is downward row operations. B plus on the right is column operations, but it's upper triangular, so I only get rightward column operations. I get these downward row operations and these rightward column operations. And when I'm done, I don't get arbitrary matrices because nor do I get arbitrary colors in my arbitrary matrices. I only get matrices that are black and white, And this, sure. This 2 by 2 matrix up here that started out only having a 1 in it, and therefore started out, thanks, and therefore started out being determinant 0, will remain determinant 0. So, so the ideal defining this matrix Schubert variety, 1, 3, 2, is in fact the determinant of that that northwest matrix. Up 2, 1 here, 1, 2. Okay, and now I'm going to do this anti-diagonal init. So this guy is this determinant is the product of those minus the product of those, and the initial term I'm going to pick out the anti-diagonal term. So that's going to be this M21, M12. Okay, so that's my degeneration. You could maybe picture it, if you like, that one of these variables equal to 1 or whatever, as something like a hyperbola degenerating to just the union of two lines. So this thing was defining an irreducible variety. The equation here didn't factor. Now it factors, so it's broken. Okay. So what I'm going to do is index the two pieces that I got in this case with these pictures. If M21 is 0, I'm going to put a cross where it's 0. M12 is 0. I'm going to put a cross there. And every place where I don't have a cross, I'm going to put elbows, or what Lamley and Shimizuno call the bump. I'm going to put in the bump. Okay. And the thing to observe is that if you follow 1, 2, and 3 and see where they come out as 1, 3, 2. So what's a pipe dream? It's something made, so the way I'm going to have it right now, it'll be something made of crosses and pipes. It'll have 1, 2, 3 up to n here, and pi of 1 down to pi of n there. When I say a pipe dream is 4 pi. And finally, no two pipes cross twice. And the coordinate space, the only coordinates that I use are where I have elbows. So in this case, I have this 8-dimensional space where I don't use the M21 coordinate. So that's something I knew about degenerating this guy to a union of coordinate spaces. And you get to you get corollaries to this. To this. You get corollaries to this theorem, which is if you think about this guy living inside matrix space, well, it has this action of t cross t from the sides. So you should decide that it's giving you an element in the equivariant cohomology of matrix space. And this says this degeneration is equivariant with respect to the t cross t. So how do you actually do a degeneration of this sort? Come up with this. You you start digging into your matrix from the northwest. As you hit a variable, you put a parameter t on it, and then you let t go to 0. And the terms that have those t's in them are suppressed. When you take when you take any single determinant and look at at what's going to live longest, it'll be the anti-diagonal term when you're digging away from the northwest. So that's how I'm doing my degeneration, but scaling a single matrix coordinate in that way commutes with left and right multiplication by diagonal matrices. And so that's why this is going, I could compute the T cross T equivariant class now, or I could compute it after I degenerate and get these pipe dreams. And then I just need to say, so okay, this guy is a ring, it's a polynomial ring in 2n variables for the for the 2n dimensional tori that are acting. And once I have a single pipe dream, I just need to say what's the equivariant class associated to that, and it'll be a product over the crosses of x sub the row minus y sub the column. Okay, so this is this pipe dream formula for double Schubert polynomials, which are the classes of these matrix Schubert varieties. Okay, so that's a degeneration you could do to this guy and understand this variety very well. I want to do a similar thing to the E-pis themselves. And so theorem, let's so from the northwest, scale the so working from the northwest, scale the matrix entry Mij by T and Pij by T inverse. So I'm going to have, I've got pairs of matrices that for right now I'll call M and P. So are these n by n matrices. And it's actually Pji, Pji by T inverse. So while I'm going to be shrinking these coordinates in my original matrix space, I'm going to be expanding them in the dual space. When I say dual, in the second space. If you think that where you could motivate this by deciding that when I'm talking about pairs of matrices, maybe that's that I'm thinking about the cotangent bundle to one space of matrices. I'm not going to make use of that picture too much, other than to say that it motivates this sort of limit, in that this limit is, in that this action is symplectic. It's preserving the symplectic structure on that cotangent bundle. I'm just doing T. I'm going to do it one coordinate at a time. So when I'm doing a lexicographic, or at least what I was doing here was in my first space, what's going on in this theorem, where I think about coming from the northwest. You could say I'm doing a lexicographic Grobner degeneration. I guess if I said lexicographic, I'd really want to say come from the northeast. So lexicographic Grobner bases, you say, I want this variable as much as possible. And then once I've maxed out on that, I want this next variable as much as possible. And if you do that from the northeast, you'll again pick out the anti-diagonal term of any single determinant. No. I'm scaling. I'm going to do this to this coordinate at the same time as I'm doing it to that coordinate, and then to this one at the same time as I'm doing it to that one. So I'm putting on a T here, and then taking T and T inverse here, and then taking T to 0, and then I'm putting it on a T here and a T inverse there, and taking T to 0, and I'll just be digging away from the northwest here at the same time as I'm digging away from the northwest there. But what's happening here is I'm doing a revlex degeneration, and here I'm doing a lex degeneration. Right. So far, this is just a sequence of degenerations I'm going to do. And I'm going to say, as we take the limit, or the init of E-pi, and this theorem, now this stuff is joint with Paul Zinn-Justin. Init of E-pi is, and we don't quite have the theorem we want yet. So I'm going to say up to lower dimensional junk. Okay? Up to lower dimensional junk is equal to a union of some guys I'll call F delta, where delta is a generic pipe dream for pi. So here was the ordinary definition of pipe dreams. So what do generic pipe dreams look like? And at some point I need to tell you more about F delta too. What a generic pipe dream looks like, you can have crosses, you can have bumps, you can also have empty tiles, in fact completely empty tiles. So here are the 7 possibilities. They go from south and west to north and east, and you might have 0, 1, or 2 many pipes in them. And you need to connect 1, 2, 3 up to n, the pi of 1 down to pi of n. And there's no condition on, you don't have to avoid these. So Bumpless pipe dreams, which I didn't define yet, don't have any of these, but we do. And there's no condition about pipes crossing twice. If they do cross twice, you just follow them and see whatever it is that they want to do. So there's, in just the ordinary theory of pipe dreams, there's this definition of non-reduced pipe dreams that do allow pipes to cross twice, but following the pipes is a tricky thing. You follow them until they cross once, and then when they want to uncross, you pretend they didn't. Okay? And now you let them cross and uncross. It's fine. Right, I haven't defined F delta. So where I don't think I'm going to write down exactly the equations for F delta, but we have them. Where F delta is a linear and quadratic complete intersection, invariant under all Mij gets multiplied by a parameter at the same time as Pji gets multiplied by the inverse parameter. So this is an n-squared dimensional torus acting on the cotangent bundle of matrix space. So what happened back here when we had just one matrix and I was doing this degeneration was I started out with something that was only invariant under the left and right action of this n-dimensional torus. But as I worked my way through the matrix entries one by one, I got things that were more and more invariant. And when I was done, I got something where every component was invariant under the gigantic torus that scales all of the matrix entries independently. And so the only possibility for such a thing then is a coordinate space, or maybe some schemy coordinate space with some fuzz on it. But the important part of our theorem was that there was no fuzz, that we got a reduced limit when we took this degeneration. I haven't defined it yet. I'm still working at this. So so what we know here, though, is we have this guy that lives inside the product of two matrix spaces, and it's invariant under only half as much as you would need to absolutely nail it down. But if I told you that I had somebody that was invariant under all this and it satisfied some linear equation, you know what those linear equations have to be. So the linear equations say that some mij is 0, some pij is 0. And I'll be a little more specific than that in a second. But the quadratics are, you can take sums of mij times pji, right? Because the product of these is invariant under this torus action. So you can take some combination of these to be 0. And that's what the equations for F delta actually look like. I'll be more specific in a minute because I think actually I got a lot of time. So what these are about, this is where, so usually I don't end up with enough time to actually get these equations, so I'm not totally sure I have them off the top of my head. I think you get these where you have a cross or a vertical or a horizontal. And you get these where you have elbows or single elbow or single elbow. Okay? And so these, let me come back to these after doing an example. There is, if you also exchange pi for W naught pi inverse W naught. So, yeah. So, okay, where there's an asymmetry is here, lex versus rev lex. So maybe it's time I get into Bumpless pipe dream to say, I mean, okay, before you degenerate, you can look at this and say, well, you can just look at this guy and say there's a symmetry if you exchange pi for pi inverse conjugated by W naught. Then you could also swap the two factors and conjugate both of them by W naught. So you find out, for example, that E-pi as a variety is isomorphic to E W naught pi inverse W naught. But that symmetry involves swapping the two factors, and I'm treating the two factors in a fundamentally different way here. So after I degenerate, you shouldn't expect to see such a symmetry. Like, I mean, I think what you're asking for is how do I take the generic pipe dreams for pi and turn them into generic pipe dreams for pi, W naught pi inverse W naught. And I don't think that there's an easy way to do that. So the very simplest version of that question is going to turn out to be getting a bijection between the pipe dreams for pi and the Bumpless pipe dreams for pi. And there is a bijection, but it's due to Daoji Huang and Yibo Gao. But it's not terrible, but it's more like on the level of one of these insertion algorithms like RSK or something. It's not just, oh, take this thing and transpose it, take a complement. It's a well, right. So they say it definitely is. They definitely do seem to have the right answer, but um, but they only specify that answer as a process. And we've got plenty of such processes in algebraic combinatorics, and it's nice when you don't have to have one, but they do so far. Okay, so what happens if so I said, let's take E-pi, and I projected it to the first factor, and I got a matrix Schubert variety, which is pretty much what I get if I project to the second factor also. But I projected to the first factor, got a matrix Schubert variety, did this did this revlex degeneration. Well, whatever. I did one, I guess if I'm going from the northwest, I did this revlex degeneration to do this antidiagonal thing. And you could ask, what if you think about this degeneration, but you don't worry about the m's, you just worry about the p's? And the answer is you get Bumpless pipe dreams. So theorem, let me put it, I'll get you the first theorem, is that you can compute these same things we were worrying about computing, these x-pi bars, as elements as these double polynomials. You can compute these as a sum over Bumpless pipe dreams. So what do they look like? They have 1 through n down here, and pi of 1 through pi of n over there. And they connect them up some way using the empty things with 1 and things with 2. And I'm missing, sorry, things with 1 and things with 2, but they don't allow the bump tile. Okay, and they say so they insist so they're almost like they're not quite like our generic pipe dream for 3 reasons. One is they don't have bumps. Another is that they're rotated 180 degrees. And the third is that no 2 pipes cross twice. Right? So, and then somewhere over those, and they take the product over the empty tiles of x rho minus. Okay? So that looks a bunch like what I was doing here, where I was taking a product over the crosses, but for them it's the empties. Yeah, it's a different formula for the same thing. Yeah, which is the double Schubert polynomial. So this class, this double polynomial in 2 sets of variables, that's the double Schubert polynomial. So this is the older formula from like Fomin-Kirillov 94 and or Fomin-Stanley maybe. No, I think Fomin-Kirillov. And this is the much newer one. Yes, so so Daoji has a separate paper in which she takes these two and says you obviously can't match up pipe dreams with Bumpless pipe dreams because the individual terms don't match. If you set all the y's equal to 0, then they would. But we can do better than that. She says, let's label every cross with x or y. And So she ends up with this theory of labeled pipe dreams. But then that's what you get if you take this guy and you expand it into monomials. And now you want to know that labeled pipe dreams are in bijection with labeled Bumpless pipe dreams. And that's what she bijects. So she does get a bijective proof of that equivariance statement. So the question is, are there any cancellations? And the answer is no, because the y's are always coming in negative. So if you just flip the sign on the y's, then it's obviously a positive formula. Yeah, and you recover. Yes, so the thing that's going on with the double, with the y's equals 0, restricts to the single. So what is my result going to be compared to that? It's going to, yeah, so let me state it with just a little bit more equivariance, because it'll make it easier when I then want to. I'm going to give a formula for the class of E-pi as a sum over these guys, and it will and it will imply both of the individual formulae. So so how's that supposed to work? So so here's this lemma. Let's say you have some variety z living inside v cross w, and on v cross w you have circles acting individually, and this guy is invariant under that. So I guess I want to call it biconical. Then that means that it therefore defines some class in the C cross times C cross action on here, which I will say is a polynomial ring in these two variables. So this defines some homogeneous polynomial in two variables. And the lemma is that if you project to V this guy Z and ask what's the class of that, then that will be the leading coefficient. So this guy is just the degree of this projection. The leading term, the leading coefficient, coefficient of the leading term in A. And meanwhile, of course, if you project it to W, then you get the same thing, but with B. So when you project this guy to V, it becomes just conical. And when you have something conical in a vector space, you say it's the cone over projective variety. And that's what we're computing. We're computing, in doing this, we're computing the degree of that cone. So this guy living inside two spaces, you can use it to compute these two degrees separately. One tiny thing you could get out of this is that the degree of x pi bar is the number of Bumpless pipe dreams. Because every single, I mean, it's about setting the y's all equal to 0 and the x's all equal to each other. And then you just get a monomial in times an expected power of x. The degree of the coefficient on the monomial is the degree of that variety. Whereas here we would get that the degree is the number of pipe dreams. Okay? So I want to get a hold of both of those using my space E-pi that lives inside matrix space cross matrix space. And I think that's going to be here. So the corollary of this statement is going to be that the class of E-pi is a sum over generic pipe dreams of there will be a to the number of equations on mij's, b to the number, excuse me, sorry, this guy I want inside. So I'll have the t cross t. I'm also going to have these guys that are dilating the two matrices individually. So this is not a faithful action, but that's okay, of matrix space squared. So I'm going to get a big product, and there will be terms that look like a plus x row minus y column, and b minus x row plus y column, and a plus b. And that's going to be depending on which kind of tile I have. And I don't want to write it down right now and be wrong. If you look for the slides for this talk that are on my homepage, where you see commuting scheme and generic pipe dreams, then you'll find exactly when you get one or the other. Okay, but anyway, this is a formula for this thing, and now we know what we're supposed to do with this formula, which is to take the leading a term or the leading b term, and if you take the leading a term, then you get pipe dreams, and if you take the leading b term, you get Bumpless pipe dreams. Yes. Yeah. The sum is over generic pipe dreams. So what's going on in that sense is I'm degenerating this guy, E-pi, to this big union of these quadratic complete intersections. You take those quadratic complete intersections and you try projecting them to the first factor or to the second factor. And some of them will project and have largest possible dimension, and other ones will project and they will drop dimension a lot. And that means they will contribute less. So if you say which of them project and keep their dimension maximally, the answer is the ones for ordinary pipe dreams. So pipe dreams here, I'm talking about ones that they only have elbows on here. They've got nothing down there. And up here, they've got pipes that don't cross twice. Here, I'm talking about Bumpless pipe dreams that do this sort of thing. And so these are generic pipe dreams, but you see they're off 180 degrees from the way Lamb-Lee-Shimizuno thought about them. And why are they off by 180 degrees? Because of this, these W naughts. No, because this is a corollary about the degree or the cohomology class, and the lower dimensional junk doesn't contribute to that. Yes. Yeah. So this does. The question was, do I need to get rid of this before I can state that? And the answer is, this is good enough to get this statement, and then this is good enough to rederive both of those. I mean, in some sense, the derivation of what's going on here isn't so different from the means by which these were derived. So you wouldn't, in that sense, want to do this first as a clean way to get a hold of those. It's just that, what do I want to say? these guys are only seeing the two extremes, the limit of A and the limit of B, and there's all sorts of stuff in between. And that's also worth worrying about, I think. If you go back to this question a moment ago, I was talking about degrees, then you'll get, and you go back to the thing I had at the very beginning where the commuting scheme, you find out you get this degree of the commuting scheme. And again, I don't know exactly that I have the equations right of the commuting scheme, but for the degree purposes, I don't care, is going to be a sum over Bumpless pipe dreams of 2 to a certain power. And so there had been no positive formula for this before. This was computed just directly up to n equals 4 in 1993. And then Paul and I, by other means, got it up to, I think, n equals 11 with previous work we did on related things. But with this formula, you can go much further. It's been in the, so that's how Paul and I met. That I wrote this paper on the commuting scheme, and he was studying a certain Markov process I'd be happy to tell you about. I mean, it's after 5, but he's studying this Markov chain and comes up with these numbers, looks in the OAIS, and it says, well, I don't know the 8 numbers that the physicists are coming here with, but the first 4 of them are the degree of the first 4 commuting schemes, which is 1, 3, 31, 11, 45, and so on. And so it comes in with those, and so then he writes Nolan Wallach and says, why are our numbers your numbers? And Nolan says, no idea, but I did just see this talk by Alan Knutson on the commuting scheme. They look in my paper and they find that that they're computing not just the degree of the commuting scheme, but also of various other E-pis. So they actually had something for every chord diagram in the disk, of which there's 2n minus 1 double factorial, whereas I only had things for bipartites, of which there's these n connect to those n factorial. So so their problem was more general than this thing about E-pi. And then we wrote a paper, and then we met in person. In that order. Right. So the question is various properties that Schuberts have. What's the corresponding properties here? So so first off, so Schuberts have one stability property, which is you embed Sn into Sn plus 1, and the Schubert polynomial doesn't change. But that's only true if you embed Sn into Sn plus 1 by putting a fixed point at the end. It's not true if you put them in and you put a fixed point at the beginning. So there's 2 ways to fix that. One of them is with these backstable Schubert polynomials that I invented after thinking about, some stuff with the Grassmannian, but then that appeared first in the Lamb-Lee-Shimizono paper. So you can get things to be sort of stable under both expansions. And there's another way that I think is more suitable for these, where you work with some sort of ratio, and you end up with things that are only polynomials in the inverse variables, actually, to get something that's stable in both directions. Anyway, so the stability is already pretty weird with these. Another problem with these is that they are all the same degree for any given n, namely their degree n squared minus n, being the codimension of E. So there are at least operators like the divided difference operators that will get you from one to another. And as I said here, there's a really easy place to start where the polynomial is just a big product of linear factors. And so you can start with that one and then apply these operators and get and at each end. And the fun thing about the operators is that they square to 1 instead of squaring to 0. I don't know any sense in which they want to be the basis for a ring, and therefore a sense in which they should get multiplied and be expanded back in that basis. So I don't have much to conjecture there. Yeah. So we came upon this from Yang-Baxter points of view. The main thing to realize what's going on, if you think in those terms, is that there are n plus 1 many possible labels. There's these n numbers, and there's also the blank. And then there's stuff where you could do where you'd say, what if I didn't have any blanks at all? What if I had 1 through 2n or 1 through a plus b? I could be on rectangle and connect like that. And so things are, in fact, easier if you don't have any blanks. We know more stuff, though it gets a little technical if you have all different letters. So one thing that's annoying is if you start saying, well, I could just call this n plus, I could just upgrade this n plus 1 through 2n, n plus 1 through 2n, and figure they're going to connect up. Well, that's not true, because since pipes can cross twice, there's lots more possibilities once you distinguish those. So that's really irritating, it turns out. But yeah, in terms, to say, to say what's going on as we go from here to there, I want to say at each square we're putting in an R matrix that satisfies Yang-Baxter.